Okay. Can you see my board? Yes or no? At least this much.
Yes, sir.
Okay. So what we are doing? Can anyone remember what we are doing? What we are doing?
Sir, we were doing a theorem.
Which theorem? Which theorem? Cauchy-Kovalevsky theorem, right?
Yes, sir.
Okay. Let me recall first because it's all. I think you don't remember anything. Let me recall. Okay. First, we start with this theorem. What is that? Let f be a real valued function analytic at the origin. Then the ODE has a solution analytic in an open interval containing 0. So we start with this theorem that let f be a real analytic function. That means this f is given to be a real analytic function at the origin. Okay, and the equation is satisfied by u is u prime t is equal to f of ut, and at u equal to 0 is 0 has a solution analytic. Then this equation has a solution analytic in an open interval containing 0. Okay, this is a very simple. You can say it's a very simple Cauchy-Kovalevsky theorem for ODE. Okay, very simple. This is the simplest ODE one can think of. Okay. Okay. Now tell me, anyone remembers the proof? How we do it? How we did it? So first we assume that suppose, just to have a recall, that suppose U is a C infinity solution of the above, means the last above ODE. Why I can assume that U is a C infinity solution? Can anyone tell me? Yes or no? How? Last time one.
Because it.
Bolo. Yes.
Because it is analytic. Because it is analytic, so it is differentiable.
So what? U is not analytic, right? See, we have to show that f is a real analytic function. You have to show that u is also real analytic. You cannot assume that u is a real analytic. I have just assumed that u is a, let u be a C infinity smooth solution of the ODE. Why I can assume this? Why?
Well, sir, we can differentiate again. So
yes.
U prime is given to be FUT, so we can differentiate again, and by it is a composition. So
yes. That's very good. So using that, since given that f is real analytic, that means f is a C infinity function. Hence, we can differentiate u prime t and u prime t, and we can go on like that. Suppose if u is a solution, of course there is a solution, because this is a standard ODE. This is by Picard's existence theorem. One can have a solution. Now we claim that this solution is a C infinity, but we have to show that the theorem. The beauty of this theorem is we need to show that this solution is in fact a real analytic solution. C infinity, you already know that C infinity, all C infinity functions are not analytic. Yes, the opposite is. The other way around is correct. If it's a real analytic, then it's obviously a C infinity function. Okay. Okay, that we assume. In the next, just I recall the step. We are given u0 is 0. U prime at 0 is given to be f of 0, just using the equation. Okay, then we did u prime of t is f prime of ut, u prime of t. But u prime of t, we know that f prime of ut into u prime of t satisfies by ft. So f of ut. Okay, so u prime of t this. So u double prime at the point 0 is nothing but f prime at 0 into f of 0. So similarly, we compute that u triple prime 0 is nothing but, if I am not wrong, f prime of 0 f0 square plus f prime 0 square into f of 0. Okay, so in general, we have written a nice thing that u nth derivative at the point 0 is some polynomial, nth degree polynomial in f0. See, you can just see f0 f prime 0 dot 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 f of n minus 1 at the point 0. Okay, where this is a very interesting point where Pn is a polynomial in n variable with coefficient in Z plus. So next step, anyone? So what will be the next step? What was the next step? What was the next step? Consider the series t to the power n. Now my claim is that this is a very important claim. Claim is that the above series has a positive radius of convergence. Clear? The above series has a positive radius of convergence. Okay, so in proving this, I'm not going to prove that. So we have constructed a new kind of function, right? G, a G function, which is, you remember, we constructed a new kind of such that it is satisfied by G nth derivative at the point 0 for every n. Okay. So next, and we know that how to do that, and we have done this. Okay, so this was the simplest example. Now let me go to another example, another theorem we did in the last class, which is a bit complicated. What is that? You remember, anyone? Anyone remember? What was the
Like if I
theorem?
have a real analytic function, I can always measurize this function.
That was a one interesting lemma. That was the majorization and things. So a very important theorem we did.
Yeah, basically we did Cauchy-Coollis in PDE form.
No, not in a PDE form. Cauchy-Coollis
Yeah,
is a system of ODE. Just now we have what we recall is that just a simple ODE. Now what we did this let me recall that, because this is important. This I will use now. Okay, let me recall this. Let AI, JK, and BJ be defined then system of PDE del uj by del xn. This is summation I equal to 1 to n minus 1 k equal to 1 to m ai j k at the point xm xn minus 1 xn minus 1, and let's say u1 u2 to un del uk by del xi plus bj. u1 u2 un, then j equal to 1 to m with the initial condition, with the initial condition uj equal to 0 and xn equal to 0. 1, 2. That means this plane, let's say this is a plane, let's say Rn minus 1, this is xn positive, this is the plane, this is xn equal to 0. Along this plane, and just you can think about what happened in x2. So uj's are given to be 0, okay, has a unique real analytic solution in a neighborhood of the origin. Is that clear? Just click on. Let ai, jk and bj be defined. If these are the, you can say, functions defined on Rn minus 1 plus m, okay, and is analytic at the origin. Both these ais and this bj are analytic at the origin. Then the system of PDE, then this is sorry, system of ODE, or you can, yeah, this is a system of first order PDE. Of course, this is ODE, not PDE. Sorry, first order PDE. Sorry, because the partial derivatives are involved. Sorry. So then the system of first order, because the order of the order is 1. Okay, the first order PDE, this has a unique real analytic solution in a neighborhood of the origin. Is that clear to all of you? What happened? Is that clear to all of you? Is the system of first order PDE. Is that clear? What happened? Hello? Am I audible?
Yes, sir.
Is that clear? Huh? Yash, clear? Manish, Vishwa, Mani,
Yes, sir.
Sagar,
Yes, sir.
Ekans, Anshu, Shammi, is it clear? We did this, right?
Yes, sir.
Yes or no? You have to say at least yes or no. Please. Huh? What happened?
Yes, sir.
The statement is clear. Given this AJK, AIJK and BJ, given these two real analytic function, this system of first order PDE with this initial condition has a solution, has a real analytic solution in neighborhood of origin. Okay. Can anyone tell me how I can prove this this uniqueness? Huh? How can I show that it is unique? Unique real analytic solution? How? How? What happened? Are you not able to follow or not? What is the problem? Tell me today. What happened? Otherwise, I will not move. Tell me what happened. What happened? What is the problem? Tell me. How I can show uniqueness? If you don't tell me, then I will not move. You have to tell this. Yash, tell me.
Sir, the proof of this is not so clear.
I am not asking the proof. I just say the uniqueness. Suppose you have a real analytic solution. Then how will you show that it is unique? So you haven't studied
like,
this thing, right? Yes, Shami, tell me.
Maybe we can we know that we can convert a PDE into we get characteristic equations corresponding to one.
That you are saying that the existence, right?
Yes, sir. So from those characteristic equation, we know if those corresponding functions are basically Lipschitz, so we can invoke Picard's theorem. Since they are real analytic, so I can kind of bound them and make them.
If you understand the proof where I have taken a particular kind of series representation, okay, and then we convert that problem to a equation of characteristics, and we studied, of course. But I have in the beginning only I have stated that there is a series type of we want to show that there is some series type of representation. From there you can't get the uniqueness. This is a PDE. PDE may not have a unique solution. So something, suppose I have given you there is a real analytic solution. Okay. Then how to show it is unique? Suppose this PD has a real analytic solution with this initial condition. Then you tell me how I could able to show that this is a unique real analytic solution. How? In case of O, I haven't say anything unique. Here how will I say? Here I cannot use the Picard's theorem. Right? How? Suppose suppose U1 and U2 are the two real analytic solutions. What will happen then? Huh? What will happen?
Then their difference will satisfy the homogeneous kind of system of AD.
Then can you recall some theorem for real analyticity? If d alpha of f at the point x naught is equal to d alpha of g at the point x naught for all alpha, then f equal to g. Yes or no?
Yes, sir.
Sir.
Yes. What happened? Yes or no?
Yes, sir.
So which point I have to use this? What is that point? Huh? Where I can, what is that function I have to use? In which function I have to use? I have given you a hint. Suppose I have given U1 and U2 are the two solution of this PDE. Then what will happen? Okay, you think about it and let me, you can come with a solution next day. Okay? This is only happened because of some property of real analyticity you have to use. Okay? Yes or no?
Yes, sir.
Is the proof clear? Yeah, or I have to repeat this proof again. Hmm? You haven't studied anything, right? Yes or no? You haven't studied anything, right? This way, how can I go, man? You haven't studied anything. Tell me, Yash,
Yes.
Shabbi, you haven't studied, right? Anyway, whatever you like, you do. Have gone through. Please go through the proof in the next class and tell me. Let me know if you have any issues. Then I will explain you again. Anyway, whatever you do. Okay. Let me do today Kovalevsky theorem for higher order PDE. Okay. Okay. Cauchy Kovalevsky theorem for higher order PDE. Okay. First, let us do an example. Okay. Let us start with an example. The Cauchy problem. Consider the Cauchy problem. Wx is equal to Cr r minus y minus aw pwy plus 1. This is given w 0y equal to 0 has unique real analytic solution. Okay. The problem is that you know what is that wx is given to be Cr by r minus y a minus w b w y plus 1. R is any parameter and w is dou w by partial derivative of w with respect to x, and it is given on the w 0 y equal to 0 has a unique real analytic solution. Let me solve this problem. Okay. First of all, let define a new function gyz is Cr by r minus y minus az. You know what is g. I have just taken this. Okay. Then can you tell me if you what is the characteristic how to solve this? Huh? Can you tell me how I should approach for this for 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 solving this problem? What should be the natural approach? What should be the natural approach?
By taking characteristic curve.
Exactly. Good. So what are the characteristic equation? Can you tell me immediately? The characteristic. Huh?
Dx by dt is equal to 1.
Exactly.
Dy by dt is equal to minus dy by g by z.
Very good.
And dz by dt is equal to g by z.
Very good. Okay. Okay. So just note that I have to solve this, right? Note that dy by dt plus b dz by dt. What will equal to? Dy by dt plus b into dz by dt. What will be? Dy by dt, this, just see these two equations. Dy by dt plus b into dz by dt is equal to
0.
So what will happen? This implies y plus bz is equal to s using the initial condition. Okay, and x ts equal to t. Okay. Now, so this is equation 1. Let us see equation 2. This is equation 3. Therefore, we have to find z, right? Therefore, integrating third equation this equation. Okay, what I will get? Dz by dt is equal to g of y into z. What is y? I have know that. What is s minus bz comma z, right? That is equal to, we know what is g. Just plug in this g of this. Instead of y, you assume that y is s minus bz comma z. Then you will get cr by r minus s plus bz minus az. Okay, so you obtain dz by dt is equal to cr by, because our main aim is to find z, right? R minus s plus b minus a into z, and z 0s is c. So I can solve in this way. R minus s plus b minus a z dz is equal to cr dt. I can integrate both sides. I will get crt is equal to 0 to t r minus s plus b minus a z prime tau theta. Okay, just from the above I get. Okay, if I do the integration, it is very simple. R minus s z, I can write z into z tau is half into derivative of z square. If I write that, then by first fundamental theorem of integral calculus, I will get half into b minus a, and I have to use this property into z square. So I will get, so this is r minus s is, what is r minus s? So yes, it is right? Am I doing any mistake? Is that correct? Yes.
Yes.
Yes, I can write something. Yes. No. No, that's all. Just a minute. R minus s z Just a minute. I have to substitute this s. Yes.
S was y plus bz.
Y plus bz, right? Y plus bz, right? Huh? Yes or no?
Yes,
S
sir.
into z plus half into b minus a z square. So I will get r minus yz, okay, r minus yz minus bz square, okay, plus half into b minus az square. If I do that calculation, I will get CRT is equal to r minus yz minus half into b minus az square. Okay, good. Okay, therefore zt is, if you just calculate zt, you can use the, you know how to do z square in this variable, a plus b r minus y minus root over r minus y whole square minus 2 into a plus b CRT. So this implies z of xy. We know t is x. A plus b r minus y minus r minus y whole square minus 2a plus b crx. Okay, so this solves the equation. So is this z is real analytic? Is z real analytic? Huh? Now 0. Yes or no? Yes or no? How to show that? Not for all, everything, right? You have to break this. You have to break this square, like x minus half kind of thing. When you can write, you know how. When you can take x to the power half common, y minus y by x to the power half. When 1 mod x is strictly less than 1, you can expand this series, right? Yes or no? You can expand this series. Yes or no?
Yes, sir.
And you can show that z is a, you can easily show that z is a real analytic function around 0. Okay, this is just a simple example. Of course, this type of example also arise in the proof of this theorem. In this theorem, we have to prove, we have to find solution to some real analytic function. If you remember, then that is
So here,
yes, tell me.
like, so in the right hand side of was a previous slide where we considered the PDE.
This one?
No, sir. The first slide where we
So,
yes, so here it should yes, so that's that slide.
This one?
This previous one.
This
Yes, sir.
one?
Here, yes, sir. Here. It should be b of like partial derivative of w with respect to y on the right hand side.
Yeah. This is wy. Okay.
Yes, sir.
This is w with respect to y. Yes, not wy. Okay. That is why you can write this. Right? Agreed?
Yes, sir.
Yeah, sure. Anyway, so it's clear, right? Okay. Now I will do Cauchy-Kovalevskaya for higher order. So in next class you should come up with a proof of uniqueness, confident proof of uniqueness. Okay, for that first order one. Now I will do or higher order PDE. Consider the problem. So today we will finish this chapter. Anyway. Where x prime is the x1 xn minus 1 variable. Okay, with another condition is a of this multi-index a, the coefficient is non-zero. Okay, now find R such that the problem meets real analytic solution in X. How to do this? Of course, A naught, A alpha, these are all real analytic. All are given to be real analytic. How to do this? Huh? Huh? Yes, yes, go on.
We can transform it into some simpler form.
Yes, very good. Which simpler form?
Take, derivative.
First order linear PDE.
Yes.
And
Very good. Very good. Let us introduce the following function. Introduce the following u del u by del x1, all possible, del u by del xn, del square u by del xn 1 square, all possible up to del k minus 1 u by del xn k minus 1, all possible. The components of u, these are the components. A vector, this u is a vector, right? The components of u are all the partial derivatives of small u. These components of u are all possible partial derivatives of u of order less than k. K is the highest order. You just see mod alpha equal to k. K is the highest order. Okay. So I am considering the vector u with all the components are the partial derivatives of u of order less than k. Is that clear? Strictly less than k up to k minus 1. Okay. Let number of components is 1 to like this m. Let m hereafter denote the number of components of capital U, so that this map U is a function each x for each x, so it's a function from Rn to Rn. What is this M? M is the number of elements in this component, number of components. So M hereafter denote the number of components also. U is a map from Rn to Rn. So this is a vector valued function, right? With Rn, Rn is the point x because U is defined on x. X is a form space variable. So U is a map from Rn to Rn. Okay. Also from the given hypothesis, capital U is equal to 0 for mod x prime less than r with xn equal to 0, because just from the given hypothesis U all possible derivatives are 0 for x prime less than r and xn equal to 0. That means somewhere here this is 0. Okay, now you tell me, it's a very important thing I am asking you. Just now you have to compute small u x n. This is like this. This is, let's say this is u1, this is u2, like dot u3 dot up to un. Okay, so I am asking you, we have to calculate d u x n k. How to do this? For k, one dot up to m minus 1. Up to m minus 1, we can compute del u k by del xn. We can compute this quantity in terms of u x j equal to 1 to n minus 1. Is that clear? How we can do this? Because if you check that, just see a toy problem. Just see a example. You consider first order one. I equal to 1 to n ai xu. Just you will understand what I am. This is very important to understand. B xu equal to 0. Simple problem. U of x1 dot up to xn minus 1 comma 0 is given to be g of x1 x2 dot up to xn minus 1. Now you tell me how we can compute the del u by del xi for I is strictly less than n. How I can compute? Del u by del xi is nothing but del g at the point 0, this at x1 dot up to xn minus 1 comma 0 is nothing but del g by del xi. Yes or no? You agreed or not? What is derivative of u for at the point x1 dot xn minus? What is del u by del x? I can compute from here. Yes or no?
Yes, sir.
We can compute because I is strictly less than n. So I can compute. Now my question is, how we can compute del u by del xn at the point x1 x2 dot up to xn minus 1 comma 0? How we can compute? Can we compute through this relation? Yes or no?
Like,
No?
sir, we know ux1 up to uxn minus 1.
Just
so we
consider
can
this problem. Just
first
consider this problem. So u is given to be the initial condition of u is given to be the x1 x2 dot xn minus 1 comma 0. At the here it is given the value of u x1 dot up to xn minus 1 comma 0 here equal to some g of x1 dot up to xn minus 1. Here the value of u is given. So I can derivative. But the problem is now I have to derivative del u by del xn with respect to nth, with respect to n variable. We cannot use this u to be here, right? Because this is only, what is the derivative meaning of this? Is a tangent. So everything I am deriving is this plane Rn equal to 0. Rn equal to 0 plane we can compute. So I strictly less than n, I can compute del u by del xi. But if I want to calculate del u by del xn, I cannot use this relation, right? Yes or no? You understand this point? This is a very crucial point here. Did you understand this point? I cannot compute del u by del xn from just u of x because this is the data is given to be in the Rn equal to 0 plane. I cannot compute del u by del xn. Is that clear or not? You can understand this one because this is given to be a function of xn minus 1 and this is also u is given to be 0. So how can I compute del u by del xn? Yes or no? Yes or no?
Yes, sir.
So how to do this then?
So let's say we know the first equation.
Exactly. If u is a solution to this equation, I can use here. What I will compute like this. That an x1 dot up to xn minus 1, the coefficient xn1 comma 0. If it is a solution, g of x1 dot up to xn minus 1, u of xn, this is equal to minus b, blah blah blah. And if this condition is non-zero, if this an is not equal to 0, I can compute del u xn, sorry, u xn as minus b, blah 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 by a. So this is important condition, that this is this I can compute del u by del xn provided an that at the initial point that is not equal to 0. Then I can compute u of xn. You understand? That is why I have given here this point. You see that? Okay. If this is non-zero, I can play around this. So here I have to do it in a higher order case. So same trick I have to do it in the higher order case. Okay. Instead of del u by del xn, I have to take like this. Let us define v equal to del k minus 1 u by del x to the power k minus 1 v. Now I have to compute del xn. Now I have to go to del v by del xn. Del v by del x. Using the equation, using this equation at this level, at Rn equal to 0. At this level, I can compute using this equation. Is that clear? Is that clear? Why I have given this condition? So I have to compute del this one, del k u by del k xn, because it is given to be up to this. Del k u by del xn k minus 1. I have to compute del k u by del xn to the power k. You understand? If you don't understand, at least you should understand this one, the first order case. Clear? So I can compute del the kth term del xn for k equal to in terms of this, as I do here. So I can write the system. So capital U, I can write the system as the following. So I can write. So the system can be written as. So the system can be written as, this is the del u by del xn. You just check. This is summation j equal to 1 to n minus 1 bj u x prime u xj, because I need this xn1 for everything, plus c u x prime, and mod x is less than r, and u equal to 0, then mod x prime is less than r, and xn equal to 0. So this higher order PDE, I can write as a system of first order PDE. Okay, by using this with this variable. Okay, is that clear? You can check with some 1 on 2 or 3 something. For 3 at least U1, U2, U3. You take K to be 2 or K to be 3 and then you check how to do this. Okay. Okay. Once I have written this, I can state a theorem. Assume C equal to 1 to n minus 1 and C are real analytic functions, then there exist are positive and a real analytic function U, which is a solution, to the bottom, to the above problem. The proof directly follows from our previous theorem. Follows from our previous theorem. Proof directly follows from our previous theorem. That this one. It is this one. Because this AJ is our B, C is your BJ. So del U by UJ by del xn, that is capital del U by del xn, and UJs are 0 at the point xn equal to 0. So I have proved this. So immediately the proof follows. Is that clear? So we have to transform that higher order PDE to a system of first order PDE and now apply the previous theorem. Is that clear, all of you? At least if you don't understand this complicated thing, at least you should understand the first order PDE. That's all. So if you don't try to understand this, so leave it. Okay. But at least you should remember that the Cauchy-Kovalevsky theorem holds for real analytic solution, holds for any higher order PDE. Okay. Is that clear to all of you? Clear or not? So I will wait for 2-3 minutes. You just have a look on your notes and then let me know. Is that okay? Is that clear or not? Again, you should tell me the uniqueness part. Why there is a unique solution here also. Okay? Is that clear? Uniqueness in the class of real analytic functions. Okay? Okay. Yes or no? What happened? What happened? Should I move?
Yes.
Huh? What
How you
happened
did
here?
like this BJ.
Huh. Yes, this Bj. Bj will be some this B divided by means Aij divided by some coefficient vectors An or something. Okay, you understand? Capital Bj.
Okay.
Okay. Okay. So if you don't like this theorem, at least you should at least you should understand the first order case. That's all. This one. The unique. So uniqueness you have to tell me in the next class. Okay. Okay. One more thing is there that I will only state. I will not prove that theorem. That is called Holmgren uniqueness theorem. That is why I said that uniqueness is a very important concept. So let me do that one and then I will stop today. Okay. Okay. There is something called Holmgren. I will not prove this. So do you know some function analysis? Huh? Do you know some function analysis? So adjoint of an operator or something like that? No, right? I don't think you know this, right? Huh? Do you know something like that? Adjoint of an operator or something like that? Do you know? Shammi, Manish,
Yes, sir.
you don't know, right? Okay. Okay, so I just state this theorem. I will not prove this theorem. Okay. So what we have proved, this is very important just to understand. Okay, just understand this. In Cauchy-Kovalevsky theorem, we proved existence of unique real analytic solution. Uniqueness of the real analytic solution, not the uniqueness of solution. We just proved the uniqueness of real analytic existence and the uniqueness of real analytic solution. For Cauchy problem. For Cauchy problem. With real analytic data. Now the question is, this I have to, you know, the PDE can have some other solutions. You know that. Now the question is this: I have proved the uniqueness in the class of real analytic functions. That means there exists a unique real analytic solution. Now my question is it possible to have the PDE have a CM solution or a smooth solutions or some continuous or smooth solutions which are not real analytic? Is this possible? So this is a natural question. I have proved the uniqueness. Of course, you have to tell me why the unique. The uniqueness is there in the proof. You have to understand and tell me. Okay. Okay. Now my question is, once we prove we have proved the uniqueness in the class of real analytic solutions. Now my question is whether this type of PDE possesses some other solution. By the meaning is that which are not real analytic solution, like CM, that's like some smooth solutions which are not real analytic. Okay, these question is answered by the uniqueness and the Holmgren uniqueness theorem. Then one can ask the same thing. Then one can ask the question whether the problem is the Cauchy problem has another solution which is differentiable of the order of the equation. You know what that is a classical solution of the order of the equation. So this is a valid question one can ask. So we have proved the uniqueness in the class of real analytic solution. Now one can ask whether the PDE admits possesses some other solution which is different, the differentiable solution of up to the order of the equation. This is answered. This is answered by Holmgren uniqueness theorem. I will not prove this, just a statement. Theorem. This is true for only linear PDE. For linear PDE Cauchy problem, that is for a linear Cauchy problem, for a linear Cauchy problem with real analytic data, there does not exist another, let's say order of the PDE is m, CM solution. Clear? Just this is hold for the linear PDE. For a quasi-linear, semi-linear, this theorem does not hold. So there might be possible that there are some CM solutions. Okay. So this is answered by the Holmgren uniqueness theorem, says that for a linear PDE with real analytic data, so for any PDE we know that for given real analytic data and the coefficients of real analytic, we have a unique real analytic solutions. That's guaranteed by the Cauchy-Kovalevsky theorem. Now the Holmgren uniqueness theorem states that for a linear PDE, you know what is the meaning of a linear PDE. For a linear PDE, there's a Cauchy problem with real analytic data. There does not exist any CM solution. There is only a solution. There is only real analytic solution. Which analytic solution? Of course, which in particular is a CM solution. But I am saying that another CM solution which are not real analytic. That does not. This is not possible for a linear PDE. There is only real analytic solution. Okay, there is only real analytic solution, which is guaranteed by the Cauchy-Kovalevsky theorem. Okay, so the Holmgren uniqueness theorem only states that for a linear PDE, you can only have a real analytic solution. There does not exist another CM solutions. Okay, is that clear? But this is only for linear PDE. Okay, that is called. So I will not prove, because this, for proving this I need some called adjoint of an operator, not a matrix or something. This is operators and all those things I need. So perhaps you haven't done in the function analysis course. So I will not prove. In the end of the course, if I get time, if time permits, I will give a short proof of this theorem. Okay, this Holmgren uniqueness theorem. If at the end of this course, if time permits. Okay. So that is this is the second chapter we have finished. So the second chapter what we have done is the Cauchy-Kovalevsky theorem, mainly the Cauchy-Kovalevsky theorem and real analytic functions. That means we seek a series solutions of the PDE, of our PDE, and we answer in a Cauchy-Kovalevsky theorem, and then we answer something called Holmgren uniqueness theorem. Okay, that is for this chapter 2. In the next chapter we will be doing Laplace equation. Okay, this is a very interesting and a completely new topic, nothing to do with your characteristic equation and all those things. You can say that we finished the half of the course. Now we will do a very important and very fundamental concept known as Laplace equation. So you know what is the Laplace equation. I can give you a brief introduction. Laplacian of u equal to 0. We want to study this equation. What are the properties of this equation and all those things? What are the qualitative properties and all those things? Okay, it's a very, very, very interesting PDE, this equation. So what is Laplacian? Del u. So Laplacian u is x1 square plus del square u by del x2 square plus dot 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 plus del square u by del xn square equal to 0. And u is a function from Rn to R. Okay, we want to study. So before coming to the class, I request you to have a look on this type of thing. Just review. I will do some revision for some new revision. Review measure theory. Means dominated convergence theorem, Fatu's lemma, monotone convergence theorem. Okay. Change of variable. Second is change of, change of variable. Change of variable. So what is this? This you know. Suppose lambda is a Lebesgue measure. Lambda is a. So you know Lebesgue measure in Rn? Yes or no? So A is a constant. So what is lambda? And A is a set in Rn. So what is lambda A of A? Can you tell me what is this? The Lebesgue measure of the set small a into A, capital A. A is any real number. What is that? And lambda is a Rn Lebesgue measure. So what is that? Lambda A?
A times lambda A.
A times no. A to the power n times lambda of A. A to the power n comes because lambda is a Rn Lebesgue, not n equal to 1. If it's a lambda is a Lebesgue measure in R, then A. If it's lambda measure of R to the power n, Rn Lebesgue measure, then it will come as lambda. So scaling comes out as A to the power n into lambda. Is that clear? So this type of scaling, this is called scaling argument, scaling. Please review this before coming to the class. Okay, I will do again scaling and all these things. Okay, dominated convergence theorem, monotone convergence theorem, Fatu's lemma. This type of scaling you should remember. And what else? Just let me check. Do you know something called polar coordinates? Anyone? Do you know something called polar coordinates? Huh? So after I have to integrate Rn f of dx, fx dx. How to do integrate? So for n greater than equal to 2. Do you know polar coordinates? So I can write this as 0 to infinity del b 0r f ds dr. Know this type of thing? Huh? Integration Rn fx ds I can add 0 to infinity del b 0r f of ds dr. Huh? Do you know this? Yes or no?
No, sir.
Okay. Just at least you should visualize. Can you visualize this? Integration over Rn fx ds is 0 to infinity del b 0r fx. So just think R2. So you have to integrate whole Rn. So how can I write R2? So how to integrate? So you take a, this is a del b 0r. This is a radius r. Now I suppose that union of del b 0r r equal to 0 to infinity. That means all possible circle I am taking, all possible. So what I am doing? Huh? What I am doing? What I am doing? This is equal to tentatively. That is equal to Rn kind of thing, right? Yes or no?
Yes, sir.
This is intuitive, so I cannot prove for you because this is some. It will take 2-3 classes to prove for me. This you should have done this. This is a very basic in measure theory. You should have done this polar coordinates. So when I do measure theory, I always do this polar coordinates. Okay, but at least you should feel this. What is the integration Rn fx dx is nothing but you first integrate on del b 0r and then integrate r from 0 to infinity. This should be the ds dr. That should be the integration. Okay, this is just a small idea. Is that clear? Just think of it before coming to the class. Please just think of it. Okay, I will do for R2. You know, for n equal to 2, you know how to do this. This is a polar coordinate. You know, r dr d theta, r dr d theta. You know, right? Integration R2 fx dx is integration 0 to infinity integration this f of r theta dr d theta, r dr d theta, right? Same thing we can do it for the Rn also. Okay, for any n. Okay, so this you just have a look on it. Just have a brief idea. So I will be doing this. Please review this Fatu's lemma, change of variable, and this lambda times a. Okay. Before coming to the class, please have a look on it. Okay.
Okay. Sir.
I think you find it difficult, this Cauchy-Kovalevskaya, but okay. So if you find it difficult, you can at least keep that high order Cauchy-Kovalevskaya. Okay. You don't have to understand that one. Okay. But at least you should be familiar with this multinomial real analytic functions and all those things. I hope that was clear to you, and also the first order case. Okay. First order Cauchy-Kovalevskaya and all those things. Thank you then. Anything else you want to ask me? So today we stop here, and next class, that is the chapter 3, we will do Laplace equation. Okay, this is a very interesting equation. We will see. Okay, that is all. Anything else you want to ask? Okay then. Yes.
Like the notion of maximal interval of existence. Also, we have some results over that PDE.
That is a, so we know we have in that first order case, when we are studying that characteristic, we see there is some interval where we have a solution, right? But unfortunately, we have seen we have seen in case of the quasi-linear PDE, there might not exist any interval for which it has a solution. That you remember, after some stage it intersects, right? You remember? The characteristic intersect, then we have to define the weak solution. So in general, we don't have such concept in PDE, maximal interval or something like that. Okay, type to type, problem to problem, it might have. For a linear kind of thing, you might have. Okay, but generally we don't have. Clear? Yes.
Yes, sir.
Thank you then, and please come up with a solution that Cauchy-Kovalevskaya uniqueness. Okay. Thank you. Thank you. Thank you. Stop recording.